session is special because now we have several speakers, and all of them are young mathematicians. We call such session of our seminar by Skorokhod readings due to the name of Anatoly Vladimirovich Skorokhod, who is the founder of our department, and together with Gnidenko and Gichman, the founder of Ukrainian Probability School. And it seems to me, at least from my own impressions, that Skorokhod always was a very busy man. You can often see him writing something on the paper and so on. But when you asked him about some mathematics, he always decided to stop his business and began to discuss the mathematics, by the way, in any subject, in any area. And now I think that I understand the reason, because mathematics is a very long journey. And when you do this journey, not to compile some theorems from other sources, but when you do it by yourself, then everybody is equal. And Skorokhod felt that he is now, at those time, he is equal to everybody who speaks with him about mathematics. So now our speakers will make a first steps on the very long journey, but every journey begins from the first step. So let's go, and let me announce the first speaker today, Oleksii Galganov from Kyiv Polytechnic Institute, and he will speak about limit theorems for fixed point of Ewens random permutations. Please.
Hello, everyone. I'm glad to be here, and I'm thankful for the invitation to the Skorokhod readings. And today I'd like to present my work, my joint work with Andrii Ilienko. That is the limit theorems for fixed points of Ewens random permutations. So during this presentation, we'll cover the following topics. First, we'll start with the definition of Ewens permutations, something about their history and their use cases, and how they arise in mathematics. Then we'll cover our core result, the Vogt convergence to the point Poisson process for some point processes defined with the fixed points of Ewens permutations. Then, as an implication of this result, we'll cover limit theorems for some statistics on fixed points, and also talk a bit about modeling methods that can be used to verify numerically our theorems, and also mention something about perspectives of further research. So what are the Ewens permutations? Ewens permutations are random permutations that are chosen from symmetric group Sn with a probability proportional to some non-negative parameter theta to the power of number of cycles in the permutation. So we can see this as a formula on our slide. It's known as Ewens distribution on the symmetric group Sn, and for theta equals 1, it reduces to the case of uniform distribution, which assigns probability 1 over n factorial to each permutation from Sn. As a part of history, let sigma be distributed according to this formula, and Cj of sigma stand for the number of cycles of length j in this permutation sigma. We have the following formula for probability of sigma having C1 cycles of length 1, C2 cycles of length 2, and so on. And it's originally known as the Ewens sampling formula, which originally came from population genetics and was studied first by Ewens in 1972 in his article on this Ewens sampling formula and its application to population genetics. Also, it subsequently found numerous applications in combinatorial stochastic process, Bayesian and parametrics, and so on that can be read in some references on this topic. As in customary literature, in what follows, we will denote this distribution as ESF with two parameters, n and theta, where theta is the negative parameter. And first, we look at a classic result by Recha, Barbour, and Valeriya about limiting distribution of joint distribution of cycle counts of permutations with this distribution. It says that in the limit, this number of cycle counts, joint distribution of the cycle counts is Poisson with corresponding parameters, and moreover, the limiting variables are independent. We'll focus on the limiting behavior of fixed points, and we know that from this result, we know that the total number is asymptotically Poisson with parameter theta, but we'll consider not only the count, but whole the geometry of how they allocated in the from 1 to n. So I said about some sequence of point processes, and we define it as following. So the sequence of point processes Pn is defined as a sum of Dirac delta measures centered at fixed points of unit random permutation normalized by n. So we get a sequence of point measures on interval from 0 to 1. So and specifically, we can see that the value of this point process at the interval 0 to 1 is the number of fixed points, and its limiting distribution is known. So our main question is, in which sense can this sequence of point processes converge, and what can the limit be equal to? Before we go to the core result, we need some definitions about this type of convergence that we study, and it's distributional convergence in walk topology, and you can see the corresponding definitions on this slide. It's important to mention that in case of the underlying space equal to 0, 1, this effect convergence in distribution is closely related to distributional convergence of cumulative processes in the Skorokhod G1 topology on 0, 1. And there's a theorem that is given by Karlin that in case a sequence of point processes converge in the Skorokhod topology, not the point process, but rather cumulative processes generated by these point processes, then the sequence of point processes vaguely converges in distribution, and these two statements are equivalent if the limiting point process almost surely has no atom at 0 and is simple that we can see what it means. So since the limit on core result is a homogeneous Poisson point process on 0, 1, we will recall first the corresponding definition that you can see. So briefly speaking, the homogeneous Poisson point process is a point process defined in some Borel subset of Rd, that for each Borel space, the value of this process on this subspace F is distributed according to Poisson law with some parameter that is dependent on the Lebesgue measure of this set. And also it's important to mention that for mutually disjoint sets, the value of the corresponding random variables that are the value of this point process and on the sets are mutually independent. So our main theorem is formulated as follows. For the sequence of point processes Pn that we defined earlier, we'll prove that it vaguely converges in distribution to the homogeneous Poisson point process N with rate theta, where theta is the same as a parameter of this unit's distribution. Also, as this limiting process satisfies all the equivalence condition of the preceding theorem by Karlin, then it also converges in the sense of Skorokhod topology. It follows from a well-known property of the homogeneous Poisson process that also the positions of these points are asymptotically independent, uniformly distributed, and conditioned on 10 numbers. So, for example, if we know that on some set we have, for example, 10 points of this point process, and then conditioned is when the locations are independent and uniformly distributed. And we will use this property in some further applications. We'll briefly describe the idea of a proof that is based on a theorem about the conventional distribution criterion from Kallenberg's book. So we can see the formulation of this theorem, and it's important to mention that for our application, this mentioned dissecting ring and dissecting semi-ring is simply can be the family of disjoint unions of subintervals of 0, 1, because it satisfies all the properties of what Kallenberg calls a dissecting set, that, and it also obviously ring and semi-ring. And we will also prove not the only convergence for probabilities that are in the formulation of this theorem, but also something more that we can see in the next slides. So the proof is based on the establishing.
Oleksii, can I interrupt you slightly before you go to the idea of proof? Let me ask you, you consider random permutation with special distribution. Then, do you know how these distributions are related to one to other? When we came from n to n plus 1, for example, how the next random permutation can be obtained from the previous one?
I understand the question, and it will be covered in this modeling part about specifically it's about Chinese restaurant process, that is a coupling for generating these permutations, and it will be mentioned in the further slides.
No, I see, because it seems then in this way we can even try to understand not only how the fixed point distribute, but to think how it changes, yes, from number to number to next number, yeah. Okay, so you will speak about this, yeah?
Yeah, sure.
Thank you.
So the proof is based on establishing an explicit formula for distributions of values of this point process Pn on sets in form of disjoint unions of subintervals of 0, 1, and we will show that as n goes to infinity, these probabilities converge to corresponding probabilities for our limiting process, Poisson process n. For the sake of simplicity, we will only show an idea of proof in case of this interval starting at 0 and ending somewhere between 0 and 1. And using a combinatorial argument based on inclusion-exclusion principle, we can get this explicit formula that we mentioned before. Then after some asymptotic analysis, for example, based on the Basque-dominated convergence theorem, we can prove that as n goes to infinity, we get these probabilities of Poisson probabilities for the values of our random process n on this set I. And if we go to the Kallenberg's theorem, we can see that we needed only convergence of probabilities of taking 0 and probabilities taking values of more than 1. And we hence prove even something more. And obviously, both conditions for Kallenberg's theorem are fulfilled, and it proves that our sequence of point process converges vaguely to this Poisson process n. Even though it's a self-initiating result, it becomes even more fruitful, and it's the whole title of my presentation, that we can consider the continuous mapping theorem. So if we take some continuous functions that take some point measure on 0, 1 and map to some real numbers, and they are continuous with respect to vector topology, then we automatically get the theorems for convergence and distribution for some these functionals. That are the statistics of fixed points that we mentioned. And also, in what follows, it's important to recall a property of this Poisson process that, as I said earlier, positions of its points are uniform and independent conditioned on their number. And in what follows, we will refer this property as CUI. So, as a first example, we will consider smallest and largest fixed points with some definition by hand for cases when there are no fixed points at all. And we get the convergence distribution to some random variables, continuous random variables, no, not continuous mixed random variables on 0, 1. And we can see from the accumulated distribution functions that they have discontinuous at 1 and 0 correspondingly. That is because we have non-zero probability of getting no points at all in our limiting process. Also, as the corresponding mapping for smallest and largest fixed point is bounded by the definition of convergence and distribution, we also get the convergence of expectations, and we can also have this explicit value for expectation of limiting random variables. This result can be proven using this CUI property and using explicit distributions for first and last order statistics of uniform distribution on 0, 1. As a more interesting example, let's consider spacings between fixed points of sigma n. That sigma n is a Ewens random permutation with parameter theta on symmetric group Sn. We also introduced the initial final spacing by placing virtual points at 0 and n plus 1. So in case there are no fixed points at all, the smallest and largest spacing is both equal to n plus 1. So if we denote the corresponding spacings as given in the slide, we can recall some basically known equalities in distribution that for these spacings and for independent identical distributed variables with exponential distribution. We'll further see why do we need it. For these three equalities, we can also prove the first one. It's something like combining the second on this slide and the upper equality on this slide. Specifically, we get the two equalities in distribution for smallest and largest spacing for n uniformly distributed random variables on 0, 1. So if we consider the smallest and largest spacing between fixed points of this Ewens permutation, we'll get the following limit theorem for this spacing is normalized by n. And in this case, we don't get the explicit cumulative distribution function, but we get the equality in distribution for this limiting random variables that is obtained using this equalities in distribution for spacings between uniform variables that we shown in the previous slide. Also, as I said earlier, the corresponding mapping is also bounded, and we get the convergence in distribution we have convergence for expectations of these spacings of Ewens permutation to expectations of limit variables, and it also have not so nice but explicit form as in case of smallest and largest fixed points. And as a third and last example of statistics we consider is the sum of fixed points of the permutation. And this statistic is interesting that we get the cumulative distribution function of this limiting random variable, but it's really complicated as compared to the first case. and it can be written in terms of modified Bessel functions of first kind. And also we get the Laplace transform for this limiting random variable. As in previous examples, we use UI property and some red-involved calculus to get this complicated cumulative distributional function and the Laplace function of our limiting process. Also, for this limiting random variable, we can get the density of its normalized absolutely continuous component that also can be written in terms of Bessel functions. So, and this absolutely continuous component can be considered as a distributional limit of the sum of fixed points conditioned on event that there exists at least one. Also, it's interesting to look at the plot of this absolutely continuous component, because we can see that its density is has discontinuities at 0, at 1, 2, and so on. That's all about statistics, and I said that we will cover in brief some modeling methods. Because it's computationally inefficient to sample Ewens permutations directly from SN, because as n is large, we have lots of elements in this group, and so it can be done by means of various couplings, which also can bring some useful properties. First, and I mentioned it, it's Chinese resonant process that can be used to generate a sequence of Ewens permutations. The first permutation we get is just a permutation on set with one element 1. Then we get a permutation on 1, 2, 1, and 1, 2, 3, and so on. And it's important that we sample them on a common probability space. And they are sampled by the following procedure that can be seen on the slide. But I think it may be more useful to look at the example for simple case of n equals 3, and that can be illustrated by the following diagram. So how we get all the permutations on 1 to 3 by this Chinese resonant process. So first we have only permutation on set of one element 1. Then we can obtain other one of two permutations on 1 and 2, and using these permutations we can obtain some permutations on 1 to 3 with corresponding probabilities that correspond with the Ewens sampling formula. For example, if we have this permutation with 2 cycles, then we can see that it's got theta to the power of 2 in the probability of getting this permutation. And yeah, it's this coupling is useful because we can generate like a whole sequence of any up to any n we want, and it may be useful in some applications. Another coupling is Valeriya coupling, and it only allows to construct this permutation for predefined fixed n. However, it has another useful property that using this coupling, the number of cycles of fixed length j can be explicitly written in terms of independent Bernoulli random variables that is used to construct this coupling. And for example, it can be used to establish bound for Wasserstein distance between number of cycles and limiting Poisson variable that, for example, is covered in this article by Arati, Barbu, and Valeriya. So as an example of why do we need modeling, we can check whether our limiting theorems is correct by considering the cumulative distributional functions for sampled values of largest spacing on this slide, and compare them to the cumulative distributional function of our limiting random variable, because as I said, we don't get the exact cumulative distributional functions neither for limiting random variable nor these spaces for permutations. So we can, for example, compare them in this way. Finally, if we talk about perspective of further research, we can take a look at two separate topics. First one is to get the related results for the number of shot cycles. It means that, as it was already mentioned, the number of cycles of fixed length is convergence in distribution to some Poisson random variable, and it's reasonable to expect the back convergence of some point process associated with cycles of fixed length to homogeneous Poisson process of corresponding rate on some appropriate space, as we got for the number of cycles of length 1. And another approach we can consider is looking at for some functional limit theorems. As an example, we can consider this stochastic process defined in terms of this Pn point process we defined earlier. And we already know that the one-dimensional distributions weakly converge to Poisson distribution. And we can ask a question about finite dimensional convergence or convergence in the Skorokhod topology. And that's where we need this Chinese random process coupling, because we can couple of permutations of different lengths on this common probability space, and this coupling provides us the possibility to do so. Well, that's basically all that I wanted to cover in the presentation, and some references that were used. You can also look through it. And basically, that's all. Thanks for attention, and special thanks to the armed forces of Ukraine for making this presentation possible.
Okay, thank you very much. And let me ask you such question. When you discuss the limit distribution for a fixed point, and you said that probably you will be interested in the behavior of the distribution of the cycles of fixed lengths, then it seems that we can consider the limiting Poisson-Dirichlet distribution for sizes of cycles, and then only randomly put into these boxes some points which are related to our permutation. So it looks like you can split your limiting procedure into two parts. One is to find the number, to find the limit of the number of the size of the fixed size, and another one just to throw the balls into boxes when you organize your permutation, and think which balls will go to the boxes with fixed size. So from this point of view, it will be interesting to get the result for size of the different range, but also I think it will be very interesting to relate this random permutation to the real dynamics on the, not on the space of discrete numbers, but initially on the interval 0, 1, related to dynamics. And there is a large family of large set of people who do this. For example, Hanin, you can mention Hanin, then James Norris, and other guys who study such random mappings with very simple structure, like permutation. Initially, it came from Sinai permutation of the intervals, and then get the limit behavior not only combinatoric structures, but also real points from the 0, 1. So it will be also interesting, I think. Thank you for the interesting talk. Maybe somebody have questions or short comment, please.
Yeah, I'd like to say the following. As you rightly mentioned, there should be nothing special about the cycles of length 1. your approach and proof technique should extend immediately to cycles of larger fixed size. And of course, it would be interesting to have such a result. And furthermore, for me personally, it would be even more interesting if you are able to investigate to prove some limit theorems for instance, for the number of cycles of length depending on n, some slowly growing function of n, for instance, logarithm n. So let's count the number of cycles having length log n. What can be said about this? Furthermore, what can be said about the corresponding point process? Yeah, and so I suggest that if it sounds interesting for you, then you look into this question. Maybe log n is not appropriate. Maybe log n or something like that. So let's take some of the number. Let's investigate some cycles of length, which is a slowly growing function of n. What can be said? That's it. But I liked your work. I liked your results. So my congratulations on that.
Yeah, thank you too. And I agree that that set can be also interesting.
Okay.
Yeah, maybe some words. I absolutely support Sasha Iksanov. It's a very interesting topic, and we very well know that short cycles for Ewens distribution, for uniform distributions is actually quite simple topic, and for example, the longest, the size of the longest cycle, and so on. But or when these sizes of cycles can depend on n, we can come to Poisson-Dirichlet distributions, and so on. And that is really very interesting topic. And thank you, Sasha, for this advice. We will try to make something in this direction.
Great.
Okay, maybe we have no time for further questions because now we have a next speaker, and the next speaker is Valeriya Kotelnikova with the talk small counts in nested Karlin's occupancy scheme generated by discrete Weibull-like distributions. Please.
Yes, hello everybody. I'm glad that I can talk today about my recent joint work with Alexander Iksanov, in which we investigated small counts in nested Karlin's occupancy scheme generated by discrete Weibull-like distributions. Before I will tell you about our main results, I will tell you the concept of nested Karlin's occupancy scheme, and we will start from classical Karlin's occupancy scheme, which also has name infinite occupancy scheme. We have an infinite array of boxes with numbers 1, 2, and so on, and we throw balls into these boxes with probability pk of hitting box k. We throw these balls independently of each other, and pk is a discrete probability distribution. Let's look at one of possible realizations of this scheme. At time 0, we have no balls, so all boxes are empty. Then at time 1, we take the first ball and throw it into one of these boxes. For example, it can fall into the box 100. This happens with probability p100. Then at time 2, we take the second ball and throw it, for example, into the box number 2. This happens with probability p2. And we proceed this procedure. The most important characteristics of this infinite occupancy scheme with n balls are the number of the index of last occupied box, Mn, the number of boxes containing at least E balls, which we denote by K of E, and in particular, we highlight an example where E is equal to 1 because we obtain the number of occupied boxes in this case. Next variable is K star of E. is the number of boxes containing exactly E balls. Sometimes these variables are called small counts, which gives a name to our today's talk. And the number of empty boxes within the occupancy range, Ln, which is equal to the length of occupancy range, Mn, minus the number of occupied boxes, Km. Let's calculate these characteristics for our particular example. At first, number of occupied boxes, K of 1. This number is equal to 3, and this boxes has numbers 2, 3, and 100. Then, the number of boxes containing at least 2 balls is equal to 2 because this boxes has numbers 2 and 100. And the number of boxes containing at least 3 or more balls are equal to 0 because we don't have any boxes with 3 or more balls. K star of 1 is equal to 1 because we have only one box in which there is exactly one ball. This box has number 3. K star of 2 is equal to 2 because we have 2 boxes with numbers 2 and 100, which has exactly 2 balls, and all others, K stars, are equal to 0 because we don't have any boxes with 3 or more balls. The index of last occupied box, M5, is equal to 100, and the number of empty boxes within the occupancy range, L5, is equal to the length of occupancy range, 100, minus number of occupied box, minus 3. So we obtain 97. These characteristics can be also understood in such way. Let Xk and so on Xn be independent random variables with distribution Pk. We can consider Xk as number of box into which fell K's ball. Then Mn is the maximum among these occupied boxes Xi1 and so on Xn. Kn is the number of distinct values among Xi1 and so on Xn. K of E is the number of distinct values among Xi1 and so on Xn, which we met here at least E times. The fact that we met here at least E times will mean exactly that there are, we mean that there are at least E balls. And K star of E is the number of distinct values among Xi1 and so on Xn, which we met exactly E times. It means that in this box there are exactly E balls. This version of the scheme has named deterministic version, and there is another version of the scheme which is called Poissonized. Denoted by pi of t, a Poisson process on the negative half line of unit intensity, and denoted by S1, S2, and so on, its arrival times. That is, pi of t is the number of such k's for which sk is not greater than t. In Poissonized version of the scheme, the nth ball is thrown at time Sn in comparison to deterministic version, where the nth ball is thrown at time n. As a conclusion, in the Poissonized version, at time t, we have pi of t balls, and in comparison to the deterministic version, where at time t, we have an integer part of t balls thrown. Why do we consider this more complicated Poissonized scheme? Why deterministic scheme is not enough? Denote by pk of t the number of balls which fall into the box k in the Poissonized scheme. Then the number of all balls pi of t is equal to the sum of numbers of balls into distinct boxes. By the thinning property of Poisson process, pk of t are independent Poisson processes of intensities pk. And in the Poissonized version, the number of balls which fall into different boxes are independent according to this thinning property, in comparison to the deterministic version, where the numbers of balls which fall into different boxes are dependent. This explains a common approach which is used for solving problems for infinite occupancy scheme and for nested Karlin's occupancy scheme. At first step, scheme is Poissonized, then we solve problem for Poissonized scheme, and then we return to deterministic scheme. So we depoissonize our result. This infinite occupancy scheme was investigated by many contributors. You can see an incomplete list of them here. I want to make some comments about some of these works. You can read about the most valuable results up to 2007 in survey by Knedin, Hansen, and Pittman. As I said previously, this scheme has also named classical Karlin's occupancy scheme in honor to Karlin, who at first investigated the scheme in 1967. In 1989, Dudkov proved a one-dimensional central limit theorem for number of occupied boxes Kn. He showed that this Kn, centered by its mean and normalized by the square root of its variance, converges to standard normal distribution under some assumption. In 2016, Chibunin and Kovalevsky proved functional limit theorem under the assumption that pk is regular varying at infinity. And this year, Iksanov, Kablutchko, and me proved the same functional limit theorem, but under the assumption that pk is slowly varying at infinity. We will return to this work today because our talk is a continuation of this aforementioned work. Now we are ready to talk about nested Karlin's occupancy scheme. Denoted by pk discrete probability distribution. At first, we have an ancestor, which we denote by empty word and put that its weight is equal to 1. This ancestor constitutes zero generation. This ancestor produces an infinite number of offsprings with numbers 1, 2, and so on, and with weights p1, p2, and so on. These offsprings live in first generation. If we interpret individuals of the first generation as boxes and will throw some balls into them with probability pk of hitting box k, we will obtain correct classical Karlin's occupancy scheme in the first generation. Then each individual k1 of the first generation produces an infinite number of offsprings which live in the second generation. These offsprings has numbers k1, k2. And we postulate that the weights of these offsprings are equal to the product of pk1 and pk2. All offsprings of the individuals of the first generation constitute the second generation. We can calculate the sum of weights of individuals of the second generation is equal to 1. So we conclude that pk1, k2 is also a discrete probability distribution. If we forget about the first generation and interpret individuals as boxes in the second generation and throw some balls into them with probability pk1, k2 of hitting box k1, k2, we will obtain classical Karlin's occupancy scheme in the second generation. The subsequent generations are formed in a similar way, and the weight of kn plus first child of some individual k1 and so on kn is equal to the product of mother's weight and pkn plus 1. In such way, we constructed a tree of weighted branching process with deterministic weights. What happens in nested Karlin's occupancy scheme? At time 0, we have infinitely many balls in the ancestor. Then at time n, for each positive integers n in the deterministic scheme, or at time n in the personalized scheme, one of the balls which are in the ancestor independently of the previous n-1 balls arrives and falls into the box k1 of the first generation with probability pk1, and simultaneously into one of children of box k1 of the second generation. Let us denote this child as k1, k2 with probability pk2, and at the same epoch into the box k1, k2, k3 of the third generation with probability pk3, and so on indefinitely. And we say that the box is occupied if it was hit by a ball on its way over the generations. This nested Karlin's occupancy scheme was first provided in the aforementioned work by Iksanov, Kablutchko, and me. The main result of this work is denote for positive integers j and n as k n of j the number of occupied boxes in the jth generation when n balls have been thrown. And the main result is a functional limit theorem for this vector valued process k n of j, properly normalized and centered under some assumption. To show you our main results, we need to provide some notation. Denote by pk discrete probability distribution, and consider counting function rho of sequence 1 over pk, which is defined as number of such case that pk is none less than 1 over x. Denote for positive integers e, g, and n as k and j of e, the number of boxes containing at least e balls in the G's generations when n balls have been thrown, and the same characteristics but with star, the number of boxes containing exactly e balls in the G's generation when n balls have been thrown. Our first result is assume that for all positive lambdas, some non-negative beta and some slowly varying at infinity function L, limit condition 1 for counting function rho holds. If beta is 0, we additionally assume that L is eventually non-decreasing and unbounded. Then we prove that as t tends to infinity, matrix-valued process depending on k of L, centered by its mean and normalized by some function, converges weakly to matrix-valued process ZL of J in the product G1 topology on D and N. Here D is a Skorokhod space. What do we have in the denominator here? Zj is some constant, you can see formula at slide, and gamma here is Euler gamma function, and fj of t is a function which has such a look. What do we know about limit process ZL of j? We proved that the rows of this process are independent copies of some vector valued process ZL. And for this process ZL, we proved that it is centered stationary Gaussian process with covariance function, which you can see in formula 3, and cross covariances, which you can see in formula 4. Let me make some comments. At first, why do we have here such strange normalization? Because usually we normalize by the square root of variance. We prove that variance of this random variable behaves as some constant multiplying by a function which we have in the denominator. So we can rewrite what we have proved in more natural way. Instead, the change in right-hand side will be that we multiply our process on beta L in power -1/2. But our first notation was more convenient for us because in such way our formulas looks more static, and the main advantage is that it's convenient to us to have common normalization in all our limit theorems, because at some step of our proofs we need to subtract our result, and it's convenient that we have the same denominators everywhere. Another comment. I want to talk a little bit about our assumption. The denominator in formula 1 is slowly varying function. If we will replace it by arbitrary slowly varying function, we will obtain the definition that function rho belongs to the Dehaene class pi. It is known that every function which belongs to the Dehaene class pi is slowly varying. So we conclude that counting function rho, which satisfies our limit condition 1, is slowly varying. And hence we say that sequence pk is slowly varying at infinity. Does exist any distribution for which limit condition 1 holds? In aforementioned paper by Alexander Kavluchko and me, we proved sufficient conditions under which a given probability distribution pk satisfies limit condition 1. And an example of such probability distribution is discrete Weibull-like distribution. That is, all pk's are equal to some constant multiplying to exponent in this power. For some alpha from 0 to 1, and C here is the normalizing constant, which guarantees that sum of all pk's is equal to 1. We can check that limit condition 1 holds by direct calculations. Function rho of t will have such look, and we can find that beta is such constant, and function L of t is also some constant. Our next result is, under assumptions of the previous theorem, we prove that as t tends to infinity, matrix-valued process depending on k star of L, centered by its mean and normalized by the same function, converges weakly to matrix-valued process XL of J in the product G1 topology on D and M, where this process XL of J is the difference between ZL of J and ZL plus 1 of J. And in particular, it means that the rows of this process XL of J are independent copies of some vector vector process XL, where XL is a centered stationary Gaussian process with covariance, which you can see in Formula 5, and cross covariances, which you can see in Formula 6. Let me also make some comment about this result. This corollary recovers result obtained in paper by Berber and Gnedin in 2009. They proved a multidimensional central limit theorem for small counts k star of E under the assumption that pk is slowly varying. We proved functional limit theorem, and from our functional limit theorem, this result implies. Let me give you an idea of our proofs. At first step, as we said, there is a common scheme of proving such results. At first step, we personalize scheme, then we solve problem, and then we depersonalize the scheme. So first step, there are no surprises, is personalization. We replace n with pi of t. Pi of t here is Poisson process on the negative half line of unit intensity. For positive integer j, we denote by pk1 and so on kj the number of balls which fall into the box k1 and so on kj on the gist level. Then we conclude that the number of all balls pi of t is equal to the sum of numbers of balls into distinct boxes k1 and so on kj. By the thinning property of Poisson process, the summands here are independent Poisson processes of intensities pk1 and so on kj. Then the number of boxes which contain at least L balls we can represent as the sum of indicators that in box K1 and so on Kj there are at least L balls. And according to this thinning property, these indicators are independent. On the second and third step, we solve problem for Poissonized version of this scheme. On the second step, we prove weak convergence of finite dimensional distributions. Let us denote entries of our matrix valued process X as KL of J, and our aim is to prove such convergence. To do this, we use Kramer-Wolf device in order to work not with finite dimensional matrices, in order to work with linear combinations of their coordinates. And key to our proof is Lindebeck-Feller central limit theorem, because we represent these linear combinations as sum of some independent random variables and apply Lindebeck-Feller central limit theorem. On the third step, we prove tightness. To do this, we apply sufficient Billings-List condition in terms of moments, which you can see at slide. These two steps, weak convergence of finite dimensional distribution and tightness, give us the desired result. And we are left with depersonalization of our scheme. We do it with the help of continuous mapping theorem. Now we know that our limit processes X and Z are centered stationary Gaussian processes. We know their covariances and cross covariances, but this information is not enough for simulation purposes. That's why we provide integral representation for limit processes X and Z. To do this, we need first some notation. For positive integer E, denote the E-dimensional back measure. And also we will consider measure P, the distribution of sequence UK, where UK are independent random variables with uniform distribution on 0, 1. We denote by W a Gaussian white noise on such domain with intensity measure, which is equal to the product measure of one-dimensional back measure and measure P. And for positive integers L, we denote by WL the restriction of Gaussian white noise W to such domain. That means that formula 7 holds. Our next theorem is let WL be a sequence of consistent white noises, which we defined just now. And for positive integer L and real U, we put that XL of U is such integral of such a function. Then we prove that XL is centered stationary Gaussian process with covariance and cross covariances, which are exactly the same as our corollary. So this integral representation fits for our limit process. According to corollary, it's written here that XL is the difference between ZL and ZL plus 1 for positive integers L. Equivalently, we can rewrite it in such way. In aforementioned previous paper by Iksanov, Kabuchko, and me, we provided an integral representation for limit process Z1. You can see this integral representation on slide. So it is natural to expect that the integral representation for ZL will be the difference of integral representations for Z1 and sum of integral representations of xk. That proves our next result. For positive integer a and real u, put that ZL is difference of Z1 and sum of xk's. Then then we prove that ZL is centered stationary Gaussian process with covariances and cross covariances, which are given in theorem 1. So they are the same as we need. And moreover, we proved that process ZL has a version with sample paths, which are Hölder continuous with exponent alpha for each alpha from 0 to 1/2. We need this kind of continuity because in proof of one of our results, we need this continuity. Thank you for your attention.
Okay, thank you very much. And let me ask you the following question. When you spoke about the Gaussian modeling, you proposed to us some description of the Gaussian process, which have the described covariance function, yes?
Yes.
But we understand that there are a lot of such processes. We can have a lot of integral constructions with respect to different white noises and so on. Maybe when choosing this one, you kept in mind some interpretation. Can you comment this construction?
Okay, as I thought for me, when we have some Gaussian process, to determine it, it is enough to determine its covariances and cross covariances. And in my mind, this integral representation was enough.
Yes, it's true that it is enough, but as I said, we can have a lot of different integral representations with the same covariances. It seems to me that you have such representation because it came from the initial problem. You mentioned in the initial slides that one of the interpretation of your scheme is the set of random variables xi1, xin, and some numbers which you study are the minimum one, maximum one, and so on. Yes. So from this point of view, it seems that maybe behind of your limit theorems, there is another one, limit theorem, where the elements of your construction goes to exactly to these white noises. And after this, the sums which arise naturally in your construction, the function like maxima, indicator, and other, will have a limit behavior like functionals from these white noises. And you will get with necessity such kind of representation. I think it can be interesting.
Let me, as a co-author, let me comment on this. You're exactly right. First, I don't know why Valeriya mentioned modeling purposes. We just wanted to get physical representation of this process, because any physical representation, in order to be able to touch on it, right? Because just description in terms of covariances and cross covariances, this is just some analytic description. And so our intention has been to provide any physical representation of the process. On the other hand, you're exactly right when saying that this particular form of integral representation came from the core of our problem. Actually, let me say just explain this just in a few words. So, informally speaking, the problem can be reduced, not exactly, but it's close to convergence of empirical processes. And we know that empirical processes properly normalized converge to Brownian bridges. And actually, our limit is whatever it means, but this is the integral of independent Brownian bridges. And this is exactly what is written here.
Okay.
And actually, this has been the way how originally our result has been guessed. Of course, the proof goes absolutely different way, but this relation to empirical process gave us a hint what should be expected, and this guess turned out right. But let me state once again that the arguments of proofs and all the reasoning is very different.
Okay, thank you. And now we have to switch to the next talk. And next speaker is Yannic Steenbeck from Universität of Braunschweig, Germany, with the talk of a difference approximation of coalescing diffusion flows. Please.
Hello there, everybody, and thank you for inviting me to talk about mathematics. Yeah, I will talk about difference approximation of coalescing diffusion flows. And yeah, there is a table of contents, but I try to organize the talk like a story, and you don't read the table of contents in a novel. So they did in a really imprecise way in this talk, but it's only for the sake of not getting in the way of understanding and clarity. So if you want to know something in a precise sense, just ask. Okay, so first, what are coalescing diffusion flows? And there are many more or less equivalent definitions, but I want to work, at least for this talk, with this definition. And it goes as follows. We have a family of stochastic processes indexed by a space variable u. And these are stochastic processes with time between 0 and infinity. And the one-point motions of these processes are martingales, and they are martingales with right to the joint filtration, so together, and they are E2 diffusions, and they are in particular E2 diffusions with no drift, but diffusion coefficient sigma, and what our sigma will exactly be will be stated in the future. And the maps, when we fix the time, are non-decreasing, so the particles don't cross. And the quadratic covariation of starting points U1 and U2 are given by this formula. And I will explain why it has to be like this in the interpretation that follows. What does this process intuitively mean? So it is just a system of particles that move like independent solutions of the one-dimensional STE we mentioned here, which is the same as saying they are E2 diffusions with this diffusion coefficient and no drift. And after they meet, they move together.
Excuse me, and BT, is it the same for all U, or you have independent Brownian motions for different U until the hitting?
So this is just more or less, they are just in distribution like this. So it is really, no, it's not the same Brownian motion. It can't be, because else they wouldn't meet. So yeah, it's just the law of the one-point motions. It's like a process that solves this SDE. And after their meeting, they coalesce, so they move together as one particle. And I made a crappy drawing of this to illustrate it. Yeah. Okay. So we assume our sigma to be very nice, and very nice means here that it is bounded and has bounded first and second derivatives, and it is actually positive and bounded away from 0. And even in this nice situation, it's not quite obvious that such a flow exists and is unique in law, but it does. And it is even somewhat nice in the sense that there's a modification such that the maps where we describe the values of the flow at a specific time are RCLL or Cutlack. Yeah, that's object we consider. So maybe an important special case that you know is the erasure flow. That's just our definition if we set sigma to be constantly 1. And here the one-point motions are just Brownian motions. So what is our goal and what was the goal of Shevchenko? Yeah, let us first consider simple SDEs of such a type, just regular SDEs, no flows involved initially. And now we have under certain regularity conditions on sigma that the linear interpolation of the difference scheme that is written like this converges in distribution to the solution of the SCE. This is known under the name Euler-Maruyama scheme. You know, it's basically just a copy of the same for ODEs. And if we now consider the scheme just not for SDEs, but for sigma coalescing diffusion flow, as we described, and then we can very informally write that our differentials of this flow are normal distributed with this covariance structure here. And so if we at least very naively copy the construction above, then we would have a different scheme, something like this, where we now replace the independent Gaussian variables by independent centered Gaussian processes that we apply to our process at the time step before, ignoring measurability issues. And the covariance function is like this. So it's really just a heuristic to explain what will happen now. So what is the problem other than measurability with this construction? If we look at these processes at time k, or the case time step, then at least for x0, we will see they are at different points. So they will actually never cross. And this is a problem because we would essentially approximate entirely independent Brownian particles and not Brownian particles that have a coalescence property. So, and the way around this dilemma is something Shevchenko published in 2011. And roughly it goes like this. First, we approximate the erasure flow, or in our case, a sigma coalescing diffusion flow, with nice stochastic flows with a smoother covariance structure, which means that the particles heal each other before being at exactly the same place. So we have a chance that the difference scheme actually knows about the interaction between two particles. And now we approximate the smoother flows by a different scheme. Of course, now one has another problem because we have to at least somewhat quantitatively control the second approximation to conclude that a diagonal sequence will actually converge in some sense to the erasure flow or a more general sigma coalescent diffusion flow. And Nishika did exactly that for the erasure flow. And what is now our hope is that we can leverage on that and show the same for sigma coalescent diffusion flows with a nice sigma that's not just constantly 1. So let us talk about the first, about the first step, approximating coalescing diffusion flow by nicer flows, not exactly coalescing. And a quick reminder, what is the Brownian sheet? So we can understand the Brownian sheet just as a collection of Gaussian random variables, which are normal, they are jointly Gaussian, so they are centered, and their variance is just the Lebesgue measure of the corresponding set. And the covariance of two such Gaussian random variables is actually the Lebesgue measure of intersection of both sets. So we have an L2 embedding. And if we somewhat informally speak about this, we can set up an integral. We can do that formally, but we can interpret it something like this. U double P. So the differentials are normally distributed with covariance dt times dp, and two of these differentials are actually independent because they have covariance 0. And this can be made somewhat formal by Ito-type isometry, exactly the same as we would do it for the Ito integral for ordinary Brownian motion. So when we now consider this Brownian sheet to formulate the following SDE, which goes something like this, where the flow will start at points exactly like the flow we want to approximate in some sense. And now we have such a phi epsilon in this integral. And this phi epsilon is just a rescaled version of a spherically symmetric test function, which has L2 or norm 1. And if we let the epsilon go to 0, then we have informally, or more or less formally in some sense, the convergence against a delta distribution. And so we hope that this will converge against our coalescing fusion flow. And actually, Dorogatsev showed this in 2004. In the sense that the L-point motions of this X epsilon converge to the L-point motions of the ratio flow. And he actually proved way more, and we will discuss that. But first, let us talk about the L-point motions. And we can more or less just copy his method because it is already general enough to prove the same for nice sigma that are not 1 and the corresponding coalescing diffusion flow. What's the basic proof idea of this for showing the convergence of the L-point motions? The usual strategy. First, we show tightness of the solutions of this SDE, and this is not too hard because we can just use the Kolmogorov criterion, and because the L-point motions of these flows are martingales with a really nice covariation and variation. So it's easy to estimate differences in LP. And what we then have to do is to show that the limit points arising from this tightness condition are actually unique. And there are many ways. And one way is to show uniqueness is to go via convergence of quadratic covariation. That's somewhat technical, but if you look at the definition of the sigma coalescing diffusion flows, the covariation structure of this was very special, and one can expect it to describe the flow very good. So, where was I? Yeah. Okay, so this is the basic proof idea. Of course, it's a little bit longer, but these are the ingredients. And yeah, now let's talk about discrete time approximations of this SDE, because yeah, let's talk about it. We consider discrete time approximation like this, which is essentially just freezing the processes over a time interval of size 1/n. So we forget about the epsilon first because yeah, just rename the file. So let's talk about this discrete time approximation first. Why is it relevant? This discrete time approximation has actually the same distribution as the difference scheme that we want to consider, because if you look at this part here and calculate its conditional distributions, maybe not in your head, then you can see that this part is actually distributed like this. So we apply a sequence of independent central Gaussian processes with the right covariance function to the process as at the case time step. So, and now if we let us a little bit more precise what our approximation wants to be, and say that we want to have convergence of the different schemes in distribution to the values of our coalescing diffusion flows at the time 1. And now if we want to pursue the strategy above and approximate this map with the diagonal sequences of different schemes, we have to control the distance between the solutions of the SDE and its discrete time approximation quantitatively in some sense. We can just focus on the discrete time approximations because we have already saw that the discrete time approximation is actually redistributed with the difference scheme, and that's enough for convergence and distribution. So now the technical part here is that Nishinka proved that at least for sigma equals to 1, that in expectation the uniform norm between uniform distance between the SDE and its time discrete approximation is actually lower than 1 over the square root of n. And there are a lot of constants hidden in this symbol, but the constant depends on uniform bounds on sigma and its first two derivatives, and the L2 norm of phi and its first two derivatives. Yeah, so this is actually an important part, but I've abstracted away from it because it's a little bit ugly, and I don't know if you have to know it exactly. So how do we show an inequality like this? First, note that both the flow and its time discrete approximation can actually be differentiated in the space variable, and therefore it suffices to just estimate at a specific point, like the endpoint of the interval where we want to compare them both, and then control the expectation of the difference between their derivatives. And this is the basic strategy, but yeah, what follows is really a wall of inequalities. And yeah, I wanted to spare you this. So yeah, let's go further. Now, how do we conclude exactly the convergence of the difference approximations? First, I said we wanted to have convergence in distribution, but that's really not precise either, because yeah, first, what objects do we have here? We already said the map for the coalescing diffusion flow can be chosen to be RCLL, or right continuous and with left limits. And the maps for the SCEs or the different schemes are actually continuous. I mean, we differentiated them. So they are, of course, RCL2. So let us talk about convergence and distribution of the space of RCLL functions, the Skorokhod space, and with time interval 0 to 1. Not time, it's the space variable, sorry. But please note, we don't look at the usual topology, the Skorokhod J1 topology, because of the following problem. We know that our limit object, because it has this coalescing property, must at least almost surely have has to contain jumps. And you can't approximate in the Skorokhod metric on you can't approximate a continuous function, a function that contains jumps with continuous functions in the Skorokhod J1 metric. So we have to consider this Levy type metric, which looks a little bit scary, maybe. But please note that convergence in this metric implies convergence at each point of continuity. And now, what is the statement? The statement is that if a sequence epsilon n has the right speed of convergence to 0, then the difference approximations corresponding to the rescaled by epsilon 1 converge to the values of our coalescing diffusion flows at time 1 distribution on Skorokhod space with this metric. And right speed of convergence means here it has to be slow enough, because if it's too fast, then our difference approximation will not be close enough to the actual solution of the SCE at this time. So, but we will see it in the proof. So what is the proof idea? As already said, we don't have to actually look at the difference approximations because they are equidistributed with the discrete time approximations of the SCEs. And so we have to only consider them. But we've seen that the expectation of this Levy type distance, which is smaller than the expectation of the uniform distance, is smaller modulo constants than 1 over the square root of n. But the constant does depend on epsilon n, because it depended on the L2 norms of pi and its derivatives. And if we do the derivative of such a function every time another 1 over epsilon will go here. So we need to talk about that, but I abstracted away about it because I don't know if you really want to see it. But this is the reason why the speed of convergence of our sequence epsilon n has to be slow enough to conclude the convergence of the expectation of this distance to 0. If we do it, if our sequence of epsilons is chosen well enough, we have this. And now finishing the proof would be possible by just proving that the solutions of the SDEs converge in distribution on this space to the map induced by the Coalescing diffusion flow. And this is something like this. One can show that the convergence of this in the Skorokhod space actually follows from the convergence of random measures induced by these maps. This is just the Lebesgue measure. And Gustav already showed this in 2004, at least for sigma equals 1. And my next step would be to show that this carries over for nice sigma that are not equal 1. So this part of the proof is not finished yet, but I hope to finish it soon. Thanks for your attention.
Okay, thank you for in some case non-formally talk, and let me just say a comment that you write that our covariance, our epsilon, cannot be too fast in going to 0 in order to have the limiting coalescing process. And non-formal reason is that if it is too fast, then trajectories of the approximation flows have crossings. Yeah. So one can think about these crossings like some one-dimensional turbulence. And Katerina Glinina, who is present here, already did some limit theorems for number of such crossings, some LDP, large deviations principle also holds. So if you will look on her papers, it will be good to understand qualitatively what is happening. And of course, it will be very interesting to construct such coalescing flow for bad sigma. Maybe it's good to check a book in Hilberto and Chorny, where there is approach where we can construct solution to one-dimensional SDE with bad sigma using local time approach, and just in order to say that we pass bad neighborhood relatively fastly. So it seems that you have a lot of questions, and I wish you to continue your investigations. Maybe some other have questions or comments, please.
I have a question.
Okay, please.
You just said about constructing this coalescing flow for bad, supposedly degenerate sigmas.
Not degenerate.
Non-smooth.
Non-smooth. You know, sometimes it can blow up.
Mm-hmm. Singular.
Yes, yes. Why not to consider, for example, like non-smooth, but 1 over x or something. You see?
See, I was wondering what's the problem because I thought about the other case and that it should be more or less straightforward. Now I see.
I just remember this very nice approach of Engelbert, and I already began to thought to unite it to our stuff with stochastic flows, where we can construct some diffusions with ugly coefficients using local times and constructing coalescing diffusion. Yeah.
I see.
Okay. Okay. If there are no any questions and comments, then we have a break.
There is. Julian Kern probably raised a hand.
Yeah, hey, thanks very much. Thank you very much for the talk. I just had a question on this metric that you use on the Skorokhod space. Is that one of the Skorokhod metrics or is it something completely different? I've not seen it yet.
I wish I could answer that, but I think the original paper was in Russian and I don't speak Russian, so I couldn't read it up.
It is difficult to find, that's true.
But you see, actually, Yannic mentioned the problem that usual Skorokhod metric is not easy to handle here, and here it is used Levy metric, which is weaker than, yeah.
Okay, so it is not the M1 metric which allows for this conversions of continuous to jump functions.
I have a remark now. It's not the metric considered by Skorokhod, none of them. It's related to the convergence of the corresponding measures.
Yes, exactly. Like Levy-Prokhorov distance.
Yeah, this is exactly. This is the weak distance between measures.
Okay. Thank you very much.
Okay. Thank you, and sorry because in my screen I haven't seen your hand. Yeah, I think that now there are no any other hand. So now we have a break up to half an hour, and we will meet at the same reference. Okay.